In this video, we will use the Arrhenius equation to calculate the temperature of a very specific rate constant. So a rate constant, lowercase k, is quoted at a specific temperature. And the Arrhenius equations relate rate constant K1 to temperature T1, as well as rate constant K2 to temperature T2. So if you know 3 out of the 4, the idea is that you can solve for that missing fourth variable, T1 at K1, K2 at T2. So the equation that sort of builds this is the Arrhenius equation, and what bridges the gap between K's and the T's is the activation energy. So the activation energy is sort of the hump. So what I've shown here is reactants going to products. All the reactants have to overcome this sort of camel-like hump, this sort of energy barrier where the orientations and the molecules must get into the right configuration before, bam, they go to products. Now they can go to products that require more energy. The products are at a higher energy state. That's endothermic. In some cases, I didn't draw that, but some cases the products are of a lower energy. We call that an exothermic reaction, when the products are of a lower energy than the reactants. Regardless of that, this is called a reaction coordinate diagram that relates how the products are related to the reactants energetically. Are they of a higher energy, in which case you need to put in that energy, or are they of a lower energy? If they are of a lower energy, then they give off that remnant energy to the surroundings. Well, here's one version of the Arrhenius equation. R is a rate constant that will be given to you on any exam. It's 8.314 joules over moles Kelvin. So let's look at this problem more carefully and make an inventory of what we need to solve for. All right, so we have a first order reaction, and its rate constant is 4.60 times 10 to the minus 4 inverse seconds at 350 degrees. Again, notice rate constant quoted at a specific temperature. So if you change the temperature, you get a different rate constant. So I'm just going to call that K1 here. I'm just making an inventory of what we have. The temperature is 350 degrees. That's T1. Let's go ahead and convert this to Kelvin really quickly. That's 623 Kelvin. And let's come back to this problem here. The activation energy is 104 kilojoules per mole. So that's EA. So it's 104 kilojoules per mole. What I'm going to do here is I'm actually going to multiply it by 1,000. You see my R is in joules per mole, so I'm going to make my EA in joules per mole. And that's really just a matter of converting kilojoules to joules, and that's just a matter of multiplying it by 1,000. Okay, so 104,000 joules per mole will be my activation energy. We have a new K2 here. What they want is the new T2. So let's plug everything in. This looks like a math-intensive problem, but let's plug everything in and make things tidy. So I'm tidying everything up here, putting in numbers into this equation. R is 8.34 times 10, 8.314 joules over a mole Kelvin. So let me put in the units here, 8.314 joules over a mole Kelvin. So you can automatically see that the moles will cancel and the joules will cancel. By the way, we don't, if you're a mathematical purist, you're not allowed to put units inside the natural log. So usually what we'll do is, it's just a math thing. So I remove the units, and then in the answer, especially if it's inside a natural log or log, you're not supposed to have units. So you put the units back in when you do the answer. But here, to this specific problem, it's temperature. So our temperature obviously is going to be in units of Kelvin, which is what we have to solve for, minus 1 over T1, which is 623 Kelvin. All right, so this seems like a mathematical nightmare, but we can piece through this bit by bit here. First of all, I'm going to calculate the natural log of this thing. 0.000460 divided by 0.000880. So that fraction, let's take the natural log of that fraction. And minus 0.6486. I'm just putting in some extra numbers here. And then our final answer should have the right units in. All right, now I'm going to take this over this. 104,000 divided by 8.314. 4,000 divided by 8.314, and that's 12,509. So let's put that in here. So as far as units are concerned, you can put everything without units with your work, and then once you get your answer, put the units back in. That's definitely an option. So, or you can just take the units along for the ride. Okay, so that times 1 over T2 minus 1 over 623 Kelvin. All right, so this is where we are at now. So there's two routes we can do here. One is we can do the distributive property and distribute this 12,500 or so times this and minus this times that, or we can divide. So I think what I'll do is I'll just divide this 12,509K here, leaving the 1 over T2 minus 1 over 623 on the right-hand side of the equation. So I'm just going to take the 12,509, divide it. All right, so let's do this on our calculator. Doing this on our calculator, let's report our answer as minus 5.185. I'm just putting some extra digits here, 4 decimals, times 10 to the minus 5 over Kelvin. Okay, I'm going to put the units along for the ride, or you can just as simply put the units in your final answer. Equals 1 over T2 minus 1 over 623K. Let's take that minus 1 over 623K and move it to the left-hand side of the equation, making it plus 1 over 623K. So minus 5.1859 times 10 to the minus 5 divided by K plus, remember I'm taking this, moving it to the other side, plus 1 over 623K is equal to 1 over T2. All right, let's do this on our calculator. So let's do this here. Minus 5.18959 times 10 to the minus 5. Here's that answer, plus 1 over 623 plus parentheses 1 divided by 623. Don't forget to close your parentheses. Okay, getting an answer of 1.55. I'll put in some extra digits here. 1.5533 times 10 to the minus 3. And now to get T2, I'll flip both sides of the equation. So I'm going to flip this, that will give me T2. I'll flip that, that will put the Kelvin in the numerator, and I got to do 1 over that to get the answer. So taking basically the inverse of both sides. So taking the inverse of both sides, taking the inverse of 1 over T2 just gives me T2. Tricky part is getting the inverse of this guy. And so inverse of this die, I have an inverse button here, x to the power minus 1, sort of like a flip it button. 643, let's call it 644K. Okay, that should be our final answer. All right, so let's go back down to here. Okay, if we flip this, this becomes Kelvin, and inverting that gives me the answer, 644 or so K. Inverting this gives me T2, so T2 is equal to 644K. So how does this stack up? Does this make sense in terms of thermodynamics? And the answer is yes. So you increase the rate constant. The only way you increase the rate constant is if you increase the temperature. Higher temperature, more collisions, the faster the rate. So this makes biological or chemical sense. That is, if you increase the rate constant, you're going to have an increased temperature. Or another way of saying it, if you increase the temperature, you should get a higher rate constant because you have more collisions, more orientations, and more chances for a positive reaction taking place.